So this is our last talk of the session and of this year's Onward. It's about an essay that is already intriguing me, and our speaker is Kartik Chandra. And take it away, Kartik.
Thanks, Stephen. I think it's the case that from time to time, we all have crises of identity. We have these moments of radical and overwhelming doubts about the nature of ourselves. I don't really know if these doubts can be externalized in words and natural language, but if I were to try, I would externalize them as questions. Questions like, who am I? What am I? What kind of person? What kind of mind? Whatever the question is, it creeps up on you. Perhaps it's crept up on you when you were deciding where to do your PhD, or deciding whom to marry, or deciding whether to forgive someone, or perhaps it was rattling around in your head when you were faced with a failure or a regret or some kind of overwhelming personal loss. This talk is about programming languages, and I promise that in about 15 minutes, these slides are going to be covered in scheme code, and perhaps that will make you all happy. But this talk is secretly also about a time that the question crept up on me. It was the spring. I was 25, and I was at a friend's apartment sitting on her couch in the sort of melancholy and heartbroken way that one can only really be in one's mid-20s, I think. And I sat there with my friend and was talking, and suddenly I felt it. There it was, the question, who am I? What am I? What kind of person? What kind of mind? And we sat there, the two of us, and we talked about these questions. And then, kind of oddly and kind of suddenly, I had this sense of deja vu. I felt like I had seen these questions before. I'd thought about them before. I'd felt like this at some point in the past. And kind of abruptly, and perhaps even a little rudely, I got up from my friend's couch, and I got on a bicycle and rode home back to my apartment. And I rushed in, and I ran to a cabinet, and I opened that cabinet, and I pulled out a stack of notebooks, a stack of journals, actually, that I'd kept for many years, ever since I was a little kid. That's a picture of me as a little kid. And I thought, okay, surely if there was a time in the past when this question had snuck up on me, then I would have thought about it and I would have written down what I thought. And perhaps if I were to read the prior work, I would have a bit of a leg up. I would have a head start on figuring out where to go from here. I thought, in short, that what these journals contained were candidate answers. Call them theories of self posited by my own mind. So I settled into my own couch in my own apartment, and I started reading these notebooks. It was maybe 9 or 10 at night. And, well, I think you can actually guess what happened, right? What happened was I started reading and immediately had this flush of embarrassment. And I looked at the writing of my 15-year-old self, and I thought, these theories are all bunk. Right? No one knows anything about themselves when they're 15. Certainly I didn't know anything about myself when I was 15, and the writing, it made me cringe, it made me feel embarrassed. And I thought, not only am I embarrassed at the object level of the writing in these notebooks, I'm embarrassed at myself at the meta level for thinking that there's any way, any chance, that by looking at something I'd written when I was 15, I could learn about myself now in the present at age 25. So I sat there feeling a little bit sheepish, feeling a little silly for having found myself in this position. And then I kept reading. I don't know what it was. Call it morbid curiosity. I don't know. I kept turning the pages. It was 11 o'clock, 12. I think it got up to like 1:30 in the morning, and I kept reading these journals. And I had this odd feeling that even though I knew that these theories were bunk, I was somehow learning something about myself. And that was weird. How is it possible to learn something true about yourself by reading theories about yourself that are false? That seemed odd, that seemed disturbing. And I sat there and I thought about it for a moment, and then it hit me. What these journals contained, yes, they contained theories of self, but also, in a sense, they contained data on the theorizer, by which I mean they contained traces left by my own mind. And if I were to look at those traces and treat them as data, like data from an experiment, then perhaps I could induce new theories, new meta-theories of my own in the present. What a strange learning mechanism this is, if you can even call it a learning mechanism. How could it be possible that it is possible to endogenously bootstrap some kind of self-knowledge from nothing? The mechanism, to be clear, is this. The mechanism is to learn something about yourself. What you do is you ask yourself, who am I? And then you make a guess. And because you're a child, you have no hope of getting it right. You make a guess and it's probably wrong. But then you look back at the guess you made and you think, well, what kind of person would guess that? And then you think, okay, well, now I know a little bit more about myself. And then you make a second guess. And this process goes on and on and on. And the theory is, perhaps by doing this, you learn something. But this should give you pause. This should be philosophically disquieting to you, because how can you get something from nothing? That seems weird. It seems weird, yes, but I've come to believe that this really is a way of knowing, perhaps even the only way of knowing about ourselves. It's as the Cartesian argument goes. In the face of radical and overwhelming doubt about the self, the firmest ground we have to build on is cogito ergo sum, reflection on reflection. Though to be clear, I don't think you have to be a professional philosopher. You don't have to be an angsty grad student to think in this way. I think every human being, every child, every baby is born and faced with this extraordinary philosophical puzzle of organizing the blooming, buzzing confusion of cognitive experience into some sort of theory of self, some sort of theory of mind. And because the strongest signal about our thoughts is our thoughts, the way forward is reflecting on reflection. Now you might say, okay, Kartik, this is a nice story you're telling, that somehow we can learn something about ourselves by thinking about our own thinking. But the only problem is, surely the primary way in which we learn is not by reflecting our own thoughts, but rather by reflecting on the thoughts of others. We learn from our teachers, our friends, our parents. We learn from authors of books. And I think that's true. Surely we learn from all of these sources. But then, where do our teachers, our parents, our friends, authors of books, where do they learn from? Let's think not at the level of an individual now, let's think at the level of a society or a culture or a community or a species. Certainly at the level of a species, there's nothing exogenous to tell us who we are. As humanity, we are born strangers to ourselves, and all we have to go on is our own reflections. This, I think, is the history of human thought. The history of human thought is people. By people, I mean painters, I mean scientists, I mean writers and philosophers, people articulating theories about what it means to be human, and then looking back at theories of the past and learning from them and saying something new about what it means to be human. I think this is this grand intergenerational baton pass that we are all a part of. Now, I want to be super clear about the kind of baton pass I'm talking about here. I'm not talking about the mechanism by which we refine theories of the world over time. So I'm not talking about the mechanism by which, let's say, Galileo articulates some theory of how bodies in the world move, and that theory is refined by Newton, which is then refined by Einstein. I think this mechanism is interesting, important, deep, and beautiful, but it's not what I'm talking about today. What I'm talking about today is the mechanism by which Galileo articulates a theory, and then someone like Thomas Kuhn looks at that theory and uses it as a case study on the theorizer, as a case study on the human mind's capacity for making theories at all. as Kuhn did in his book, The Structure of Scientific Revolutions. Or as Alison Gopnik did when she reflected on Galileo's theorizing as a case study to make an analogy to how children learn about the world in her book, The Scientist in the Crib. I'm talking about sciences here, but I think this happens everywhere. And I think, in fact, the strongest examples come to us not from science, but from art. I'm thinking of a painting whose title is Where Do We Come From? What Are We? Where Are We Going? By Paul Gauguin. And of course, the title of this painting is just another way of saying the question, who am I, what kind of person, what kind of mind? This painting hangs in the Boston Museum of Fine Arts. It's actually not very far from MIT, which is where I go to grad school. And I have spent so many hours of my graduate career sitting on the bench in front of this painting at the Museum of Fine Arts, looking, thinking, yearning, wishing that perhaps if I looked at this painting long enough, I could read off an answer to the question. Because after all, isn't this canvas really just a theory articulated by Paul Gauguin, a theory as to who we are or what we are? The only problem is I don't think that I can take this theory seriously. And the answer, and the reason for that is, well, if you're not in the know, Paul Gauguin is kind of a controversial figure. The scholarly consensus on him is that he brought with him a racist, colonialist, sexist attitude towards the subjects he painted, who were the native people of Tahiti. He saw them as savages who had to be civilized by the Europeans. And I can't take seriously a theory of what it means to be human coming from a person who saw other humans as less than human. That just doesn't click for me. And so I think that this theory must be bunk. But then again, at the same time, I look at the man who's looking at this painting and I think surely he is learning something about what it means to be human, but how is that possible? It must be possible because this painting, yes, it articulates a theory of what it means to be human, but it's also data on the theorizer. It teaches us something about our own capacity to look out at our fellow people and see not people, but something less. And that, in turn, I think, allows us to induce new theories of what it means to be human in the present. Okay, so I have articulated for you a candidate learning mechanism, a way by which human beings might learn something about themselves by reflecting on their own reflections, either in the mind of an individual in the here and now, or the mind of a species over its history. But surely by now, you are very, very uncomfortable, perhaps skeptical, perhaps about ready to get up and walk out of this talk, because of course, like, how could it possibly work this way, right? Like, this just seems circular and wrong and bizarre. In fact, let me offer you 3 reasons why this just seems completely implausible. Reason number 1 is what I call the circularity objection, which is there's no such thing as a free lunch. You can't get something from nothing. How is it possible that with no exogenous signal, a mind can just bootstrap endogenously some sort of self-knowledge? That just seems impossible. That's the first objection. The second objection is this empirical observation that our best AI systems certainly don't work this way. If you take a large language model and you train it on its own output, it does not attain enlightenment. It does not learn about itself. It actually starts decomposing and producing gibberish as output. That's an empirical objection. And then there's a representational objection, which I will just read out verbatim because I think it is phrased so poetically. This is from Emerson Pugh, who writes, "If the human brain were so simple that we could understand it, then we would be so simple that we couldn't." I accept all of these counter-arguments. I think these are valid objections. I think they're thoughtful, and I think they're forceful. But I've been around you people, I've been around PL researchers long enough to know that when in the face of reflection on reflection, when in the face of this kind of meta thinking, it pays to be a little cautious. It pays to be a little open. I have learned to be skeptical of things like a set that contains itself or a machine that simulates itself. All sorts of weird things happen there, and I've learned to be a little wary of a compiler that compiles itself. These objects defy our intuitions, and so I'm willing to be surprised in this case as well. But if I were to be surprised, I would like to do so through the wide eyes of the programming languages researcher. And so what I'd like to think about is, as a programming languages researcher, what's the minimal model of this kind of endogenous bootstrapping of self-knowledge? And I think, of course, whatever this minimal model is, it must be a program. But what kind of program? Okay, well, I think it's a program of whom we demand the question, who are you? Which is to say, what is your source code? And okay, the program then is forced to guess its own source code, but of course, in the beginning, there's no hope. Like, it doesn't know. We are born strangers to ourselves. So the program makes a guess. It thinks I'm X. And X is probably wrong. But then we ask it again. We say, okay, what is your source code? And by the way, the first time I asked you, you said that you were X. And that little bit of information should allow it to learn just a little bit about its own source code. And it should make a better guess this time. It should say, well, given that I previously guessed X, I now think I'm Y. And then, of course, we can keep going. We can say, okay, again, who are you? And let me just say, the first time I asked you, with no information, you said you were X. And when I asked you who you were, and also said that given X, you guessed Y, and I also tell you that given X, you guessed Y. And based on that, the program should make a new guess, Z. And the hope would be that if we loop this over and over again, that eventually it would reach some kind of fixed point, and the fixed point would be repeatedly guessing its own source code over and over and over again. This kind of program is similar to a quine. It's similar to this type of program that prints out its own source code. But I think of a quine as like a nativist solution to the problem, right? Like if you've ever written a quine, the way you do it is by like embedding a little bit of the source code into the source code. Whereas what I'm proposing, the program that I want to write with you all, let's call it not a quine, let's call it a gauguine. A gauguine infers its own source code. It's an empiricist. It learns from its own experience of itself. So the goal of this talk is to write such a program. And that's what I'm going to do in the rest of this time. All right, what kind of program are we writing here? Well, we're writing a program that makes guesses under uncertainty about itself. And so it's not just a program, I think it's a probabilistic program. And so I wanted to start off by giving you a couple of etudes just to warm you up to the idea of probabilistic programs that make inferences about the world under uncertainty. All right, here's the first etude. Suppose you've got a friend, suppose arbitrarily she's named Quinn. Quinn comes to you holding two dice, a red die and a blue die. She shakes them up and she rolls them, but doesn't show you the outcomes. Quinn says, look, these dice, the sum is 7. And then she asks you, what is the probability that the first die came up 3 or more? You all know how to solve this problem, right? Here's how you do it. You write out the space of all possible outcomes. There's 36 of them, 6 times 6, and they all have the same probability, 1 in 36. Then you pick out or condition on the outcomes that you know are possible based on the information you have, and then you integrate over the desirable outcomes, and then you just read off the answer. The answer is 4 and 6. The probability that the blue die came up 3 or more is 4 out of 6, or 2/3. Let me show you how you'd write a probabilistic program that does the same calculation automatically. So I'm going to use a programming language called Church. And what Church is it's just scheme, but with a couple of additional primitives. The first primitive lets you set up probability distributions. So for example, we can say that a die is just a uniform distribution over the numbers 1, 2, 3, 4, 5, 6. The second primitive is called infer, and what infer lets you do is do a bunch of probability operations inside its body. So for example, given this distribution die, we can sample from it. We can say that the blue die, D1, its value is sampled from this distribution die. And similarly, D2 is also independently sampled from this distribution. Another thing you can do inside infer is you can condition distribution. So we can condition on the information that the sum of these two dice is 7. And finally, what infer actually does is it takes an expression and computes a conditional distribution over that expression. So here the expression of interest is, well, is D1 greater than or equal to 3 or not? And what infer will do is give you a distribution over possible values of this expression. Okay, this is a Boolean expression, so the distribution should be over true and false. That's what the support of the set of Booleans is. And indeed, when you run this program, here's what you get. You get 2/3 and 1/3, which is exactly the same answer as we got doing this by hand. That's the first etude. Now, here's the joy of church. The joy of church, the joy of scheme is that you don't just have to do inference over Booleans and numbers. You can do inference over any kind of object in the language, inference over pairs, lists, even programs, because code is data in scheme. So let me show you an example of how that might work. So, okay, your friend Quinn is back. Quinn shows up now with a deck of cards, and she says, look, I really like cards that are blickety. And you say, okay, Quinn, what does blickety mean? And Quinn says, shh, I won't tell you. But she says, okay, I've separated out the blickety cards from this deck, and now I'm going to show you some. And she repeatedly picks up a blickety card and shows it to you, and then puts it back, and then with replacement draws another one and shows it to you, and over again. And here's what you see. You see the king of clubs, the king of clubs, the jack of clubs, the jack of clubs, the jack of clubs, the queen of clubs, the queen of clubs, the king of clubs, the queen of clubs. And then you look at all of these outcomes that have happened over and over again, and you think, well, based on this data, what does it mean for a card to be blickety? Okay, someone in the audience, please, just could you call out a hypothesis, a theory, a definition? What does it mean for a card to be blickety? Great, thank you, person in the audience. Person in the audience says a blickety card is a face card from the club suit. I agree, that seems right. Let's write a probabilistic program that makes this inference. Okay, so how would such a program work? Well, it's doing inference over the space of possible definitions of blickety. And let's say that we're going to model definitions of blickety as little predicates, little scheme predicates over cards. So we're going to start by writing a little generator of predicates. It'll generate predicates like clubs question mark, spades question mark, or more interestingly, not face question mark, or and red question mark, not face question mark. You can see these are all just scheme predicates that can be generated by a probabilistic program. How do you write this program? It's actually not that hard. A predicate of some depth, well, the depth has to be greater than 0, and if it is, then we're going to sample uniformly from production rules in a grammar over possible predicates. So for example, the terminals in this grammar are these atoms like clubs question mark or spades question mark. And the non-terminals are these combinatorial operators, things like negation or conjunction or disjunction. And notice that you then make a recursive call to the predicate generator. Now, I want to be clear about one thing here. This does not define a uniform distribution over all predicates. Why doesn't it do that? Well, think about what it takes for this probabilistic program to generate not face question mark. You have to get lucky twice. The first time you get lucky is you pick not. And then the second time you get lucky is in the recursive call, you have to pick face question mark. Whereas if you were just generating clubs question mark, you only have to get lucky once. Just at the top level, you have to pick clubs question mark. So there's higher weight, there's higher probability of generating clubs question mark. And in fact, you can think of this generator as naturally inducing this prior where simpler predicates have higher probability than more complex ones. Okay, once we have a predicate, we need a way of taking all of the cards that match that predicate and pulling them out of the deck. That's not hard to do. Let's write this little program. Note that because it's scheme, we can use eval to convert code as data into code as code. And so that's how it works. Let's write a function called makepile. It takes as input a predicate. What does it do with the predicate? Well, it evals this little meta probabilistic program. And what that does is sample a card from the deck and condition that it matches the predicate. Great, we're almost done. Let's write the actual inference now. How does that inference work? Well, we start by sampling a predicate. And we turn that predicate into a pile of cards. And then we say, OK, well, for each card that I observed Quinn pull out of that deck, I'm going to condition on the fact that that card was sampled from our pile of cards that are blickety. And finally, we're going to generate a distribution over predicates pi. So OK, again, what this program should do is output a probability distribution over predicates. So it should look something like this, a probability distribution over predicates. And indeed, when you run it, you get the highest weight. The mode of this distribution is and face question mark, clubs question mark, which is exactly what our friend in the audience said. OK, I think these are all the tools we need to write the program that I really want to write. So let's try to write it. We're going to try to write a program called Gauguin. And what does it do? Well, it takes as input a history of past guesses that it has made, which could be empty. And in fact, on the first guess, it has to be empty because it hasn't made any previous guesses. Okay, and then what does it do? Well, it performs inference. And what is this inference over? Well, it's inference over programs. So we're going to sample some hypothesis gamma, which is a hypothesis for who I am, right? Then, just like with the cards, we're going to loop over all of the data we've seen, so loop over each H in our history, and then we're going to condition on having made that guess. So what does that mean? Well, we're going to condition on an equality between what we actually guessed and having sampled from gamma. So a sample drawn from running the probabilistic program gamma, which is our hypothesis about who we ourselves are. Okay, now we get into just a little bit of trouble because remember, gamma is a program just like us, which means it takes as input a history of past guesses, but now we've lost the pointer to past guesses, right? Gamma needs to be called with input all of the guesses that came before little h. So, okay, this is nothing we can't fix, it's just a little annoying. We're gonna loop not directly over the list of past guesses, but rather over postfixes of that list. So what does that tell us? Well, a postfix of this list is a pair, because lists are pairs, and the head of that pair, or the car of that pair, is a guess, and the tail of that pair, or the cooter of that pair, is the previous guesses, which is exactly what we want. Okay, so again, what do? Come on, buddy, work with me here. What do? We condition on having guessed that guess. To do that, we assert an equality between what? Well, the actual guess, that's head of H, and a sample from gamma, which you can get by evaling gamma, giving as input tail of H, so all of the guesses that came before guess H, and that's it. Then we say, please compute for me a conditional distribution over gamma, over hypotheses for who I am. Okay, by the way, I had in this program, the generator of programs. You might wonder what that's like. It's just like the generator for predicates. So it looks like this. Well, to generate a program of some depth, you condition on that depth being non-negative, and then you uniformly sample from various productions that define a grammar over church programs. So things like sample and condition and so on and so forth. Now, sometimes I say this, and someone objects. They say, okay, Kartik, hang on a second. Shouldn't you also be inferring program alongside Gauguin? I think that's a really incisive critique. I think that that's really perceptive, right? Like what is the status of program? Is it part of Gauguin or not? Well, I don't know, it's not clear. However, let me say this. If we were to infer program, what grammar would program be drawn from? Would it be a grammar called grammar? And then what grammar would grammar be drawn from? Would there be a grammar called like metagrammar? You see how you end up with this like little problem of infinite regress. I think this problem was most forcefully articulated by Jerry Fodor, who is a philosopher, and he wrote this book called The Language of Thought, where he argued that all human minds have this innate built-in language of thought, and part of his argument, or I think one of the most beautiful parts of his argument, is he says, well, one cannot learn a language unless one already has a language. So I think that the madness must stop somewhere. You have to truncate the recursion somewhere, and here we'll truncate it at program. Okay, that aside, that's the program, that's the Gauguin. And I just want to be clear, like this is a real program. This is not a metaphor for a program as my slides often tend to have. This is a real program that you can download from github.com and run. And I want to show you actually what happens when you run this program. So how do you run this program? Well, remember that you have to give it as input a history of past guesses. But the very first time you run it, you have not made any past guesses, and so the history is empty. So what happens when you call Gauguin with capital H being the empty list? Well, it makes the following guess. It makes this guess that I'm going to call H1, which is the simplest possible program. I call this the wild guesser theory of self. Because all this program is saying is I'm drawing samples from the prior. Like that's the kind of mind I am. When asked who I am, I just randomly guess from the prior. And of course this is wrong, right? Like this program is not equal to the program on the previous slide. However, it kind of makes sense that this would be the first guess, because remember what I said about predicate generation. I said that the way we defined it naturally induces this prior over simpler programs being more probable. And this is, in some sense, the simplest program that matches the type of Gauguin. And in fact, it is so simple that it gets guessed over and over and over again, in fact, like several times. But then an interesting thing happens. The Gauguin looks at the history of its past guesses, and it sees, well, wild guesser, wild guesser, wild guesser, wild guesser, and it thinks, okay, something here is suspicious. There might be a better explanation than that I just always randomly happen to select the wild guesser theory. Perhaps I'm a program that always says the same thing. So I call this the omniscient theory. This says I have some innate built-in knowledge of who I am. I don't know what that is, by the way, but I'm gonna sample some hypothesis gamma and say that every time I'm asked to make a guess, it's going to be equal to gamma. Now this is also obviously wrong. It is not equal to the program we wrote on the previous slide. However, not only is it wrong, it's self-defeating, because as soon as you guess H2, you've broken the property that all of your previous guesses were H1. So you guess H2 once, and then you realize there's no way this is true. And you move on to H3. Okay, H3 is an even better guess. Here, it fixes that bug. It says, no, it is not that each time I previously make a guess, it's equal to my hypothesis gamma. Rather, it's equal to a sample from gamma. This is getting pretty good. I call this the memoryless theory, and the reason I say that is because notice, look very carefully, how does it call gamma? Well, it calls it with an empty list as input. It makes the exact same bug that we were so close to making a couple of slides ago. Essentially, this program is saying, look, each of my previous guesses, it was made as if I had never seen a guess before. And that's wrong. But after observing this a few more times, it figures it out, it fixes that bug. It realizes, no, I need to loop over the postfixes, and I need to assert equality between the head and the tail and whatever. And there it is. That is the program that we wrote on the previous slide. Let me show you this in another format. So here I'm showing you this plot. Just look at the one on the left. On the x-axis are guesses, so first guess, second guess, third guess. Or you can think of it as the number of previous guesses you've seen. And on the y-axis, I'm showing you the distribution over guesses that are made. Each of these lines is one of these hypotheses that I talked about. And of course, there's many, many others, because that grammar generates lots of programs, but these are just the notable ones. And you can see, okay, well, it starts off really liking saying that it's a wild guesser, and some other theories actually make a little bit of headway, but eventually around 10 guesses, there's this, call it a paradigm shift. Something happens and it discovers, actually, I'm Gauguin. So is that success? Well, I think, yes, we wrote a program that I would say endogenously bootstraps some kind of self-knowledge. But this, again, should be disquieting, because I started this talk by giving you all of these counter-arguments as to why you could never write such a program. And I just want to take a second to reflect and think, well, how did we get around these? So, okay, here were the counter-arguments. The first one was the circularity objection. You can't get something from nothing. Except notice that there is something exogenous here. There's the program, but then there's the interpreter, and there's the random number generator, and there's the hardware that it's all running on. In the same way that there's a mind, but then there's a brain that the mind is running on. There's neurons, there's activations, and that's external to the mind. And I think that's what solves this problem. I think one way to think about this is this little quote from The Catcher in the Rye, where Holden Caulfield says, how do you know what you're going to do till you've done it? Actually, doing something teaches you something, because you don't know what you're going to do until you've done it. So something there must be external. That's my answer to the first objection. The second objection, okay, this was the empirical observation that AI models collapse if trained on their own data. So like, what's going on here? Well, notice that a large language model doesn't know that it's being trained on its own data, whereas the probabilistic program we wrote it's designed to update its belief in a model-based way. It knows that the data it's being given was guessed by itself. And I think that lets it integrate this evidence in a principled way and actually learn something in a way that an LLM doesn't. Okay, finally, Emerson Pugh, who says if the human brain were so simple that we could understand it, then we would be so simple that we couldn't. How did we get around that one? Well, here I think when we think about representations, they need not be explicit. In fact, some representations can be implicit. For example, the space of all possible hypotheses, all possible programs, is very large, but we represented it implicitly with this small grammar that generated them. And so I think implicit representations, for example, the self-representation being implicit in the conditional distribution over program and the data that it's conditioned on, I think that's how you get around the representational problem. Of course, I think it's the case that even having answered these objections, there was always the possibility that it wouldn't work, right? Like it's possible that the dynamics of the system are such that even though there exists this fixed point where it does repeatedly guess itself, you never reach it because the dynamics are just weird. And so there's something interesting here, something empirically true, something worth explaining. And in fact, I bet you all have thoughts and questions about this. As PL researchers, I can kind of anticipate what you might be thinking right now. And you know, if we were to have a lot of time for questions, I'm sure you could come up with lots and lots of really good ones. Please ask me those in the hallway. The question on my mind right now is different. It's the question, what does this program teach us about what it means to be human, which is perhaps not a PL question, though arguably it is. I think there is an answer to this, and I'd like to offer you mine. Guys, I think I'm not wrong in saying that the time we live in, the time is out of joint. By which I mean, well, I don't know if it's the decline of democracy. I don't know if it's the rise of AI. I don't know what it is, but I think we live in a time when we as people, as nations, and as a species are being faced with the question again, who are we, what kind of people, what kind of minds? But I think on top of that, there's this kind of nihilism about the question. Is it answerable? Is there an answer at all? I think we might be dangerously close to concluding perhaps not. And if that's the case, well, I don't know, I think things break down. I'm worried about this. And I think the program that we wrote, in its own tiny little way, is a kind of existence proof that it's possible to build a system, creature, mind that does, in its own tiny little way, endogenously bootstrap a kind of self-knowledge that it didn't have before. It's at least possible. And if you're willing to grant that existence proof, then I think you might be willing to say, at least it's possible for us too, we radically complex creatures, humans too might be able to learn something about ourselves by reflecting on our own reflections. And if you admit that, then you might think, well, how do we do it? And I think this teaches us that the way to do it is to look to our past, to look to history. In a time when history feels mutable, for sale, up for grabs to those with the most power and the most influence, I guess the thought I want to leave you with is the importance of looking to the past as a way of learning about us, about the importance of looking not just at the art of the past, but the history of art of the past, not just science, but the history of science, not just literature and philosophy, but the history of literature and philosophy. Thank you.